So, what I want you to imagine is that we have a line here, a number line, and that's the x-axis, and this x represents the time in seconds that the clock is off. Okay? So let's put 0 here, right here in the middle. And let's say, let's say this is 1 second off, and if this is 1 second off fast, we'll put fast this way, then being off in seconds, being slow, would be this way. And of course, we show these with negative numbers. Okay? And of course, this would be 2 seconds, and this would be 3 seconds off, right? Or 2 seconds slow, and 3 seconds over here. Okay. Now, what would my distribution of all the clocks look like? Well, imagine we just take each clock, say each dot I put here is an actual clock. You find that a clock is a little bit fast, like a half a second fast. There's the clock, we'll stack them up. So imagine Nick's clock's a little bit slow, okay? Nick's clock's a little bit fast, then he's fast and he's slow. Imagine as we test these clocks, we get lots of clocks here and we start stacking them up. And as we test more and more clocks day after day after day, and we stack them up, it may not be too hard of an understanding to realize that we're going to get something like this. And you should recognize that just as a pretty crude, but a normal distribution, where we have very few clocks that were this slow and very few clocks that were really fast, but most clocks were kind of right around close to 0. In fact, if we calculated the mean, we would say, yeah, the mean looks like it is about 0. If we also stipulate that our standard deviation is exactly 1 second, if we stipulate that our standard deviation is 1 second and that our mean is 0, then we have a special kind of normal distribution. We have a distribution that is called a standard normal distribution. Again, that is where my mean, mu, is equal to 0, and sigma, lowercase sigma, the standard deviation, is equal to 1. In this case, 1 second. Of course, just to remind you, our y-axis here, if we're doing a frequency distribution, this represents the number of clocks that are in each number of seconds off, fast or slow. But if this is not a frequency distribution, but a probability distribution, then this is some percent of the probability that it occurs. Now, there's 2 ways we can state that probability. We can say, if I randomly pick one of the clocks out of this pile, what's the probability that it'll be so much faster, so much slow? That's one way we can state the probability. Another way we can state it is, what percent of all the clocks are this much fast or this much slow? Okay? Now, there's one thing you need to realize, though. When we're talking about a normal distribution in which the values that are being measured on the x-axis are continuous values, in other words, they're not just -2, -1, 0, but all the possible values in between as well. For example, I can be off 1.68 seconds fast, or I can be off 1.43725 seconds slow. I've got continuous data values. Whenever we have that, you need to understand that the probability of any specific value is 0. Let me say that again. The probability that we get a clock that is, say, exactly 1 second off, that probability is 0. That cannot occur. There is no such thing as a clock being off exactly 1 second. We can round a continuous value to 1 second, but a clock can never be exactly any value, because we don't have the tools to measure it that accurately. No matter how accurately you measure, if you find a new tool to make it more accurate, then you say, well, it really wasn't 1 in the first place. It was actually 1.0000005. So what can we do? We can only calculate probabilities of ranges of values. I can't say what's the probability that a clock is exactly 1 second fast, but I can ask the question, what's the probability that a clock is between 1 second and 2 seconds fast? I can ask that question. I can only find the probability of ranges of values. All right. So let's go down and look now at just a distribution that's a little cleaner here. Here's a regular bell-shaped curve, standard normal distribution, because I'm saying that mu is 0 and my standard deviation is 1, sigma. Okay, and again, this is the x-axis, and this, of course, is my probability. All right. Now, we know from the empirical rule already that if we go out 1 standard deviation in either direction, in this case is 1 second fast to 1 second slow, we know that if we consider all the clocks in between here, we know that this will amount to 68% of all the clocks. And you should recall from the empirical rule that if we go out another standard deviation in either direction, that is up to 2 seconds fast or 2 seconds slow, that this will account for, let me change the colors here, if we consider all the clocks that are within this range of being fast or slow, that this will account for 95% of all the clocks. And another way to state that is, as well as being 95% of all clocks are in this range, think of it this way. If I were to randomly choose one of the clocks from here, there's a 95% chance that it will be between 2 seconds slow to 2 seconds fast. That's another way of stating the same idea. And of course, you might recall there is a third part to the empirical rule that says if I go out 3 standard deviations, then I'm accounting for 99.7% of all values, in this case, in terms of all clocks. Okay, in my next video, then we'll actually find some other probabilities using other ranges other than what the empirical rule states.